So next, Junaid Rehman is representing Lux for QCI, the national QCI in Luxembourg. He received his PhD degree in electronic engineering from Kung Hee University, Korea in 2019. In 2022, he joined the Interdisciplinary Center for Security, Reliability and Trust, University of Luxembourg, where he is currently a research scientist in the Signal Processing and Communication Group. His research interests include the quantum information sciences and that include quantum computing and quantum sensing.
Thank you very much for the kind introduction. Okay, I am Junaid Rahman. I am going to talk about the challenges ahead on the road to EuroQCI. Before going into details, let's have an overview of quantum information sciences. So there are 4 pillars involved. The first one that we are talking about today is quantum communications. The other 3 are quantum computing, quantum metrology or sensing, and quantum simulation. The simulation is sometimes absorbed into the quantum computing pillar, so we sometimes have 3 pillars, sometimes we have 4. The communications that we are talking today, by today I mean literally today on the 4th of September that we are here, we are talking about communication in the sense of a very separate pillar. But in my presentation I am going to talk about the communication, quantum communication that is going to support the other 3 pillars. That is, it is going to support the quantum computing, it is going to support quantum metrology, and also it is going to support quantum simulation. And in achieving that, what are the challenges that we see as a community? So let's have a look at the applications of quantum communications in this broader definition of quantum communications. So current day, today, we are already talking about the quantum key distribution, so we know about one of the applications quite in detail. But even the quantum communication that we have today, it is point-to-point only. If we want to extend the range from one hop to multiple hops, then we have to introduce some trusted relays, which is quite a big challenge in quantum key distribution. So anyone sitting in between has to know my secret once I use the quantum key or quantum key distributed key for encrypting my information. So that is one of the challenge. Some other present day or near future quantum communication application is distributed quantum sensing at small distances. These are also very prototypical type of examples. Some demonstrations already exist today. So this is what we expect from present day and near future. In the intermediate term, what is the next step after we solve some of the problems in QKD is the entanglement based quantum networks supplemented by quantum memory. So we are going to develop some quantum memories with limited times, micrometers, microseconds, milliseconds, something like that. And then these 2 abilities together, entanglement distribution and having some very small quantum memories, already allows us to demonstrate much more interesting applications than we can demonstrate today. For example, we can perform blind quantum computing with this technology. So blind quantum computation is something like, I am a user, I have a computation problem to solve on a quantum computer, but I do not have a quantum computer big enough. I have to delegate my work to someone else, but I do not trust that entity. So I want to keep my computation hidden, but I want someone else to do that. So that is one possibility in quantum computing called blind quantum computing. Others are also very interesting applications for the intermediate term. Anonymous quantum communication is another possibility. So we want to communicate. In classical, we have the example of something called the Tor network. So you want to remain anonymous on the network, but still you want to access the network resources. So we have something similar in quantum communication, but the anonymity guarantees are much more stronger here. Okay, so in the long term, eventually the greater vision of quantum communication that we talk about is called quantum internet. So this quantum internet has the ability to distribute entanglement on global scales with the help of satellites, with the help of quantum repeaters, and this allows us to tackle the greater vision of distributed quantum computing. So even though if we cannot build a very large quantum computer at one scale, we can, if we have a good enough quantum internet, we can combine multiple quantum computers together to tackle some problems that are much larger scale that can be tackled on a single quantum computer. Another example of this is quantum clock synchronization, which also involves entanglement. Okay, so as you look at the transition from present day to the intermediate term and to the long term, there are two things that are expanding from today. So first thing is expanding is our technological capability. So entanglement distribution, we are introducing or providing some tasks that are not possible today. So entanglement distribution is one example. And the second thing that is happening in this timeline is we are enlarging the distances between the communicating nodes. And we have already had a lot of discussion today about, not a lot of discussion, but some discussion on the possibility of satellites to help achieve this goal of extending our distances that we can cover. So I'm going to ask the question, are the satellites really required to achieve a global scale quantum internet? So some people already seem to know the answer that we definitely require quantum satellites. But what if we have quantum repeaters? So there are two possibilities. If I want to communicate on a quantum link from here to, let's say, 1,000 kilometers, I have two possibilities. Either I can use a satellite, or I can use a chain of quantum repeater nodes. So these quantum repeater nodes, as already explained by our colleagues, perform entanglement swapping in between. Okay, so if I have a very large distance, I have two possible options to cover this distance: satellites or a chain of repeaters. So the question is, which one is going to cover this distance more efficiently? Okay, so, let me remark here that this is not a problem in a quantum key distribution network, because the quantum key distribution network that we have today, at every hop we just decode the key and then re-encode. That is the task of the trusted relay node. So there is no kind of errors or losses associated with entanglement swapping here. Okay, we just decode our information into the classical domain, re-encode it and send it. So whatever distance or the rate we can achieve in one hop, in a single hop, we can somehow get kind of linearly related rate at larger hops as well. But in entanglement swapping, there is a problem. Okay, first let me show you the relationship between the satellite-based EPR entanglement sharing and the fiber-based entanglement sharing. So that is the comparison of the first example on how to achieve this distance versus the second example that I showed. The second example that I showed how to achieve this distance. Okay, so without any quantum repeater and with a satellite. So here the answer is trivial. We know that already. That if we have a single hop or without a repeater chain, if we want to cover some distance, we cannot go beyond, let's say, 150 kilometers. But the question about the repeater chain versus the satellite, it remains open. Anybody wants to take a guess just to wake you up? Okay, a lot of people expect that the satellite is going to be the right answer, and they are right. The satellite is going to perform the EPR or entanglement sharing at larger distances, and but these results, these are very contextual. Okay, so there is this disclaimer. So these results are very contextual. You have to consider what is your error rate in entanglement swapping, what is the success rate. If there is so many losses in entanglement swapping, this is not a deterministic process. When you actually implement entanglement swapping, it is very probabilistic. Maybe 1 out of 10 times you get successful maybe 1 out of 2 times you get successful. So this rate is going to dictate how well you can compete with the satellite-based approaches. And then there are also errors or losses associated with interfacing different devices. So when you are bringing your photonic qubits, can you implement the Bell basis measurement in your photonic qubits, or you want to convert them into some other form before you perform a Bell basis measurement? That is also an important issue here. Okay, but with some crude numbers, some typical values that I used, this seems to be the answer. Okay, so the second challenge I'm going to talk about here is more of a policy challenge, not a technical challenge. The policy challenge is we have already discussed today that there is an alternative to quantum key distribution called the post-quantum cryptography, and there are several security agencies, maybe the most famous is famously the NSA of the United States, that recommend not using QKD, and they favor post-quantum cryptography. I'm not sure if it goes into favor or against QKD, if the NSA is saying not to use QKD. Okay, anyways, they have some criticism, and the specific criticism involves, for example, the QKD is only a partial solution. So it only secures your keys when they are in transit over the quantum channel. What happens before that, what happens after that, how you use those keys for your encryption, this is not handled under the topic of QKD. But already we see with that from the discussion today that a lot of the challenges that are around this problem, they are being tackled, and very intelligent and very brilliant minds are working on these problems. QKD requires special purpose equipment. It increases infrastructure cost and insider threat risks. Securing and validating QKD is a significant challenge. That is also discussed today by one of the presenters, that they are working on the standardization and certification. But still, it remains a significant challenge, because if we talk about the side channel attacks, we are going to certify against the side channel attacks that are known today. We of course cannot certify for the side channel attacks that will be found in the future. And finally, the QKD increases the risk of denial of service, cord cutting, or measuring everything going on your quantum channel. It stops QKD device from working, which is also a valid challenge. But again, when we look at today we are talking about a single link between two nodes. But once we have the diversity in the links, two nodes can have multiple routes between each other. Then this denial of service is going to be much less severe as compared to what we see today. So that is the challenges that I wanted to talk about in the EuroQCI perspective. Not talking about the quantum communication infrastructure only for QKD, but also when we talk about the greater challenge of the quantum internet, which is going to be based on entanglement sharing. Nevertheless, quantum key distribution still remains a killer application of quantum internet. And before concluding my presentation, I invite all of you to think about the future when we have the capability of distributing entanglement at the global scale. When we have that capability, what is going to happen with the quantum key distribution as we know today? This is just food for thought. Maybe think about it sometime later. And of course, since this is a training event, I included some readings for the students that are interested in this great and very, very interesting field of quantum communications. Thank you very much.